Related rates. At my website, you'll find a PDF called Related Rates. You should print that out, and it looks like this. When we do a related rates problem, this is what we're going to do. First thing is write every given rate as a derivative with respect to time. Derivative of something with respect to time will equal some given number. So we're going to start with page 255, exercise 8. When a circular plate is heated in an oven, its radius increases at the rate of 0.01 centimeters per second. That's the given rate. Given rate. So it's the derivative of the radius with respect to time is 0.01 centimeters per second. Then we write the rate that is to be found as a derivative with respect to time. It's going to look like this. Right here. Derivative of something with respect to t equals question mark when blank equals blank. So we'll be writing something just like that. In this exercise 8, at what rate is the plate's area increasing? Derivative of area with respect to time equals question mark when the radius is 50 centimeters. When the radius is 50 centimeters. So look at the next step. Write a formula. This is the hardest step because we just have to think of some relevant formula or equation. In this case, not too hard. A equals pi r squared is the area of any circular plate. So that was step 3. All right, then this next step is eliminate as many variables as possible. Do not eliminate any variables mentioned in steps 1 and 2. So this step is irrelevant in this problem we're doing. But now we're going to do step 5, differentiate implicitly with respect to time. Differentiate, that means take the derivative of both sides. The derivative of the left side with respect to time equals the derivative of the other side is going to be this exponent times this number times what's in the parentheses raised to this exponent take away 1 times the derivative of what's inside the parentheses. So that's what we call step 5. And now we're up to step 6, plug in numbers. That means the dA dt is going to be replaced with dA dt, since that's what we're looking for. R is going to be replaced with 50, because we're trying to find dA dt when R is 50. And dr dt is going to be replaced with 0.01. So dA dt is what we're looking for. If we knew dA dt, we'd put a number in that spot. Equals 2 pi times 50 centimeters times 0.01 centimeters per second. Okay, so we just plugged in numbers. Plus r with 50 and dr dt with 0.01. So look at the next step and you'll see it is solve for the unknown rate and label the answer with appropriate units. Step 7, solve for the unknown rate. In this case, that would mean just simplifying this over here, because dA dt is already solved for dA dt. So 2 times 50 times 0.01 is 1 times pi is pi. There's centimeters here and there's centimeters here, so we would put centimeters squared, or square centimeters, per second. It's brought down from above, and we're done. Okay, let's now do number 14. This is on page 256. Let's see that we're going to follow the exact same steps. Inga flies a kite at a height of 300 feet. So here's the ground. Up here and somewhere there's a K for kite. Perpendicular distance from the kite to the ground is 300 feet. There's a string connecting the kite to Inga, I. The kite is flying horizontally, so the kite's going this way. That means this distance down here, we'll call this side X, that is changing at a rate of 25 feet per second. I hope you look at the words in the book so you see where I'm getting all this. Page 256. So there's the rate that's given. How fast must she let out the string? The slanted line segment is the string. We'll put S for string. We want to know how fast this is being let out. So ds dt is the rate we're looking for. When the kite is 500 feet away. That's when S, the string, is 500 feet from her. That's when the kite is 500 feet. So given rate is a derivative with respect to time. Rate that we want to find, question mark, is a derivative with respect to time when something equals something. Now we write some formula that comes out of our brain. In this case, x squared plus 300 squared equals s squared. Now we're going to differentiate each term. The derivative of the first term is 2 times 1 times x to the first power times the derivative of what's inside the parentheses. 300 squared is a constant. The derivative of the new constant is 0. The derivative of 1s squared is 2 times 1 times s to the first power times the derivative of what's in the parentheses. So that's differentiating both sides with respect to time. And now we could plug in numbers, or if you want to first divide both sides by 2, you get x dx dt equals s ds dt. We've divided both sides by 2. All right, now where the x is, sometimes in a related rates problem we draw two diagrams. This up here, I refer to this as a video. In your mind, the kite is moving. Over here is a snapshot. Video over here, snapshot. This picture, right here, I took this picture exactly at the instant when the string, when the kite was 500 feet from her. At that very instant, the kite is still 300 feet above the ground because it said the kite was moving horizontally. And at this very instant when I took this picture, I took the snapshot, this side of the triangle is 400 at that instant. So up here, this is a video because x is changing as the kite moves. S is changing also as the kite moves. So I took a snapshot at this instant. Right here, snapshot. So now we plug in the numbers. What I mean is, where x is, I put 400. Where dx dt is, we put 25. So it's 400 feet. Dx dt is 25 feet per second. And where the s is, we put 500. Find ds dt when s is 500 feet. And ds dt right here at the end, that's what we're looking for. So we plug in numbers. At the instant when s is 500, x is 400. Dx dt was given. We wrote it down up there. We're trying to find ds dt when s is 500. So now we're ready to solve for ds dt. Well, 400 times 25 is 10,000. 10,000 feet, so we'll write square feet per second, divided by 500 feet equals ds dt. Because I'm trying to solve for ds dt, so we're dividing both sides. Dividing both sides by 500 feet. On this side, we have 10,000 divided by 500, which is 20. And up here, there's square feet, and down here, there's feet. So we have canceling. We still have a feet. We still have per second. So this simplifies to 20 feet per second. Copy this down, and we're done. That's the rate at which she's letting the string out. And now we're going to do number 16 on page 256. Make sure you read the problem. Don't just listen to me read it. Sand falls from a conveyor belt at the rate of 10 cubic meters onto the top of a conical pile. Well, the rate that's given is cubic meters per minute. The thing that we measure in cubic meters is volume. So the derivative of the volume with respect to time, it is 10 cubic meters per minute. So the given rate is this. The top is cubic meters, the top is a V. Bottom is minutes, so the bottom is a T for time. The height of the pile is always 3/8 of the base diameter. The height of the pile is always 3/8 of the diameter. That's a given information. We'll probably use that later. How fast are the height and radius changing? So we're going to just do part A. How fast is the height changing? So the derivative of the height with respect to time is what we are looking for. When, there's always a when something, when the pile is 4 meters high. And the pile is 4 meters high. So given rate is a derivative with respect to time. Rate to be found is a derivative with respect to time, when something equals something. And now we are going to write the formula for the volume of a cone, because this water, or the sand, is making a conical pile. The volume of a cone is 1/3 pi r squared h. Now, one of the steps in related rates that we haven't used yet is step 4, eliminate as many variables as possible. What that means is you need a formula like this, but this formula has too many variables. It has a v, which is good, because dv dt is given. It has an h, which is good, because dh dt, we're trying to find that. We want to get rid of the r, because there's no r mentioned up here. What we do is first know that the diameter of the base of the cone and it's all the way across. That's d. The diameter of a circle is always 2 times the radius. That means the d in this information up here can be replaced with 2r. H equals 3/8 times d, but the diameter is always twice the radius. So h equals 6/8 or 3/4 r. We multiply both sides by 4, we get 4h equals 3r. That means the r in this formula can be replaced with 4h over 3. The r up in this cone formula is going to get replaced with 4h over 3. V equals 1/3 pi 4h over 3 cubed h. That's what r equals. That's what that step means when it says eliminate as many variables as possible. We still have v and h, which we need. So here's something to simplify. V equals 1/3 pi. You square the 4, you get 16. Square the h, you get h squared. And you square this 3 on the bottom, you get 9. Bring that one down. So v equals 1 times 16 over 3 times 9 times pi times h to the third, because there's h squared and there's h. So it's h to the third. So now we're going to do this step called differentiate both sides with respect to time. The derivative of the left side with respect to time equals the derivative of this side is going to be that number 3 times that number, 48/27 pi, h to the second power times the derivative of what's in the parentheses with respect to time. 48/27 can be reduced to 16/9. dv dt equals 16 pi over 9 h squared dh dt. All right, now we're going to plug in numbers. Now that we've differentiated both sides, we plug in numbers. So I'm looking to see if we have a number for dv dt. Yep, 10. I'm not going to worry about the units. It's going to be 10. Here I'm going to write 16 pi over 9. Do I have a number for the h? The answer is yes, because we're trying to find dh dt, question mark, when h is 4. So right there is 4 squared. And dh dt is what we're looking for. So copy dh dt. If we multiply both sides of this by 9, multiply both sides by 9, this side will be 90, and this side will be 256 pi dh dt. Because 4 squared is 16, 16 times 16 is 256. 256 times pi is 256 pi. And the 9 is gone because I multiplied both sides by 9. And now we'll divide both sides by 256 pi. 90 over 256 pi equals dh dt. 90 over 256 can be reduced to 45 over 128. 45 over 128. The pi is in the denominator. The h up here would be the height of the pile. That would be measured in meters. The t on the bottom is time, and that's measured in minutes. That's why meters per minute is the label for this answer, which is the derivative of h with respect to t. So the textbook says to give this answer in centimeters per minute. So here's a question. How do we convert this answer to centimeters per minute? Right now it's in meters per minute. Maybe you can find some information about the metric system and tell me how you do this. And if you would like to try part B on your own, the question is how fast is the radius changing? You can try that and see if you come up with this answer, 375 over 8 pi centimeters per minute. That's for part B, which I did not do with you.